All right, so we have already had a little bit of an introduction to our unit about thermal energy involving heat and temperature and how we measure things. And you've already done a foldable to get some of the vocabulary that we'll be talking about in these notes, so hopefully you already have a little bit of prior knowledge going into this. If you need some extra resources, the page numbers in the books that we have in class are 436 through 438, and I believe that when I was gone a couple of days ago that you guys read through these pages, but if you ever need to look back at them, they are available to you in class. So with that said, let's go ahead and get started with these notes. So the definition of heat is that it is a form of energy called thermal energy, and it's the energy a substance has because of the motion of the molecules. So because heat is a type of energy, we measure heat in joules. So we're keeping that same unit that we used before, and we would abbreviate it with a capital J. So when a substance gains heat, basically that's another way to say it's gaining energy in its molecules. Therefore, we would say the molecules are moving more vigorously. Another way to describe that is that they're kind of moving more quickly. They're trying to spread apart more because they need more room to move around. If a substance loses heat, so that means it's losing energy. And if you've ever lost some energy, your motion usually is going to get more sluggish. You're going to want to kind of sit still. If you don't have a lot of energy, a lot of times you might start to fall asleep. And so you can think of those molecules kind of slowing down, and as they slow down, they get closer to each other. Now, we've watched a Bill Nye video before that talked about absolute zero, and that's the theoretical point where all molecular motion would stop. So we know that hasn't happened yet. Scientists have gotten really close to it, but there's never been a way to isolate a molecule so that no energy can get to it. So it's not something that's actually happened. So this graph here is the phase changes graph, and this is something that we really need to understand as we're talking about how phases change from one type to another. We've talked about the 4 phase changes being solid, liquid, gas, and plasma, but in terms of this graph here, we're just going to limit it to the 3 phases of matter that water can be. So we're leaving plasma off of this graph. As an object turns from a solid to a liquid and then to a gas, the particles move faster. So that implies that we're adding heat. As the object turns from a gas to a liquid to a solid, so we're moving backwards on this graph, the particles end up moving slower because they have less energy. So during phase changes, which are the spots that are highlighted in red here on the graph, so we've got phase change here and a phase change here, the particles actually are moving the same speed until the phase change is completed. So in a phase change, the particles spread apart or move closer together. And that's what all the energy is focused on. So instead of changing how fast they're moving, they change their spacing between each other. So that's what causes a phase change. So when the particles are moving the same speed, we talked about in class how the temperature is the average kinetic energy. Another way to say that is average motion. So when we're averaging out the motion, if it doesn't change at all, that's why we see this part of the graph level out. Okay, same for here too. So phase changes, temperature doesn't change, but the energy does. And that's why we see that plane. So temperature is a measure of how hot or cold something is, and something that I want you to make a note of is, again, our definition from the book is that it's the average kinetic energy. There's not really a space to write this. So what you're going to have to do is just write it off to the side. A measurement of temperature is degrees, and then after we write the little degree symbol like that, you have to define what the scale is that you use to measure it. Here in America, we use Fahrenheit. The rest of the world, most of the rest of the world uses Celsius. And if you ever go anywhere else besides the United States, you're going to see that and probably be really confused because the numbers end up being different based on the scales. The size of the degrees, so the difference between the numbers, depends on which temperature scale we use. So we'll talk about that briefly. So Fahrenheit scale is what we use here. And hopefully you already know these points, but if you don't, freezing point of water is 32 degrees Fahrenheit, so that's why our magic number in the winter is this. And a lot of times if we have moisture on the roads and it gets below this number, That's why it's an issue for buses to be out. Boiling point is 212 degrees Fahrenheit. So if you're trying to boil water in a pot when you're cooking, that's how hot the water has to get before it'll start boiling. 0 point in the Fahrenheit scale is obviously going to be 0, but it doesn't really mean anything. But we'll find in the other two scales, it does have a meaning. So one thing that we want to be sure we understand here is that there are 180 degrees Fahrenheit between freezing and boiling points. So that means between boiling and freezing, the numbers are broken up 180 times. Okay, so that's what that means. Now the Celsius scale, there's another way to call that. I think it's the centigrade scale. Both of them start with C. Centigrade, remember cent means 100. Grade is talking about like all the little tick marks between the numbers. The Celsius scale fixes the point where water freezes as the 0 point. So you guys know how much I love Guatemala. My friends in Guatemala would say that if it was freezing outside, in terms of the freezing point of water, they know that as 0 degrees Celsius. Here in America, we know that as 32 degrees, and then we'd have to specify we're talking about Fahrenheit. The boiling point of water is set to the number 100. So that means that there are 100 degrees Celsius between freezing and boiling, and this is why it's closely linked to the decimal system. This is why we call it centigrade, because there are 100 spaces between those 2 points. And that's why the rest of the world uses it, and that's why it's in the metric system, because it's nice and neat, and it's a lot less confusing than using Fahrenheit. Finally, there's something called Kelvin. Kelvin is mostly used in physics and astronomy. We're talking about the temperature in space or on other planets. Usually they're going to talk about it in terms of Kelvin, and then they'll convert it to something that we can understand here in school, just everyday life. And what they do with Kelvin is they basically take the Celsius scale and move the 0 point from freezing all the way down to zero, absolute 0. So this point, there are no negative measurements. So you might want to make a note of this too. No negatives. Okay, so absolute 0 is 0K. And the freezing point, we still have 100 degrees between freezing and boiling points. So this makes the freezing point be like 273, and the boiling point is 373. So the degree size for Kelvin is the same size as 1 degree Celsius. And I'll show you an example to help think of this in class by showing you a meter stick on either side to make sure we get the visual for this. You might notice that there's no degree sign with Kelvin, and that's just the way they write it. Again, with physics, they don't use the degree symbol the way they do for Celsius and Fahrenheit. So here's a picture that kind of puts it all into perspective for us with these numbers. It's all measuring the same thing. We just have different numbers based on the scale we use. So this top, we need to label it as the boiling point of water. Okay, so for Kelvin, Celsius, and Fahrenheit, those are the numbers that we have to point to. The middle point here, 273, 0, and 32 are the freezing points, and then absolute 0 is set at 0 Kelvin, negative 273 Celsius, and negative 459 Fahrenheit. If there are any other temperatures that you want to see converted from one temperature scale to another, I suggest this website. You can't obviously click it, I don't think, on this PowerPoint video, but you can at least copy this address down and look at it on your own. If you also have a weather app on your smartphone, I've noticed that you can set the scales between Celsius and Fahrenheit just to see what the difference in the numbers would be when it's measuring the same thing. So that might be something you can look into. Make sure that if you have any questions from this video, you write them down so we can talk about it in class as we observe these things, and I'll see you later.